sneaky, Andrea.
Thank you very much for indulging me with fish and document cameras and stuff like that. I hope I can repay it by aimless ranting. I want to talk about where we are these days and where we're going, and about the revolution in Type Inference, which is overdue, and which is, first of all, I mean, we need to turn a whole bunch of things around, and in particular, the key thing we need to turn around is the membership symbol. Because in the future, types are proposed first, and the values which inhabit them come afterwards. Well, let's see where we are by visiting an old favourite topic of mine, the astonishing coincidence which Robin Milner managed to engineer in the definition of standard ML, which has grown to 5 different differences that are all the same in standard ML. One more since last time I gave a slide like this, because there's another distinction that it's worth drawing out. So, I mean, on the one hand, there's the distinction in syntactic categories. There's one sort of a beast called a term, and another sort of a beast called a type, and they don't mix. They're just different parsers, just different stuff going on, and you can use completely different namespaces for them and all of that sort of stuff. And then in terms of what you see in your program text, that was very carefully engineered so that what is seen is just the terms, and then the unseen things, they're not in the program text, that's the types. And a related but not totally identical distinction is the agency for the production of these things. Okay, when you work in the old-fashioned mode where you write in an editor and then you send your completed file to a type checker and you get back abuse, then these two kind of coincide. You see them because you wrote them, right? The seen things are written by human beings. And what happens when you send them to the type checker is that the type checker generates the unseen things. The machine figures those things out, and if it likes them, it says yes, and if it doesn't like them, it says no. Then what happens, on the basis that it said yes, some sort of code generation happens, and the things that were types, that were invisible, that the machine created, the machine then destroys, leaving just the stuff that you wrote, the terms, which get turned into some kind of machine code. And then, kind of off on a tangent, there's the question of what kinds of abstractions are possible. You know, which abstractions are typed. And it turns out that when you abstract over these term-like things, you have only vacuous quantification. You have this degenerate arrow where you don't name the thing being abstracted because there's no way the thing to the right of the arrow might depend on it. Whereas if, when you're abstracting over the types, the invisible machine-generated things, then all of a sudden it becomes possible to name the abstracted thing with a universal quantifier. And in the Milner world, all of these things line up I mean, astonishingly, and to a significant purpose. And what's gone wrong culturally is that we have forgotten the differences between the lines in this picture. Some of us brought up in Milner land never knew these things were even separable. There might be some way to push these things out of alignment or some reason to do so. And you can have such broken conversations where you say, I want to move one of these distinctions a little bit, and the response from the people you're with is, but if you move one of the other ones, something will go wrong. With the tacit assumption being that the two distinctions are locked together. And I've had so many brain-damaged conversations with people about dependent type systems simply because I was talking about one distinction and they assumed it would have a consequence for the positioning of a different one. So that's if I can deliver one message today, it's the distinction between these distinctions. And let's kind of see what happens when we just make this world a bit more wobbly. I actually want to sort of throw in another distinction, which, one of the problems about when we talk about type inference is that it's kind of a nebulous phrase which covers a whole bunch of different sorts of things going on. And here are two of them, exemplified by the let rule and the variable rule. I've tidied them up a bit. Here in the let rule, what happens is that first of all, we synthesize a type for the body of the let, and then we notice that there are some free type variables at the top of the context. See, that's the difference. I bother to put type variables in the context. Recommended. Variables not properly scoped by a context. What was anyone thinking? But since these variables are obviously not doing anything terribly special, it's perfectly reasonable to discharge them with universal quantifiers. So when we come to check the rest of the let, we are allowed to assume that X has had its type generalized. Okay, so what's going on here in this, in Milner's let rule is, first of all, in our program there's no clue as to what sort of a thing X has to be. And we're relying on type synthesis to work properly to figure out what sigma is. And then we're relying on somehow discovering which are the under-constrained alphas to figure out what generalizations are possible. And we're really putting quite a strain on what type synthesis has to be able to do in order to, as it were, guess the plan for X. Right? This is guess the plan type inference. Whereas what happens in the variable rule, by contrast, is that somehow we already know what X is capable of and what its degrees of freedom are. And what we're saying is, somehow choose an instance of X. And that is kind of follow the plan type inference, right? We know how many degrees of freedom X has from somewhere, and all we have to do is pick a particular instance in a particular setting. And so when people talk about whether a system has type inference, as if that's a kind of binary thing, then always be suspicious. They might not know what they're talking about. And in particular, they might not understand that there are a bunch of different things they could be talking about all at the same time. So again, message, beware of stepping on distinctions that you've forgotten exist. Okay. Let me ask the question, what makes type synthesis tricky? So I'm being phoned up at the moment. That's always great when that happens. Right, so when we were in the situation, the sort of simply typed setting with the, so here's the simply typed application rule, we've got a fighting chance. What we're seeing one use of the function. And we've got a fighting chance of figuring out the type of the function, because we know what type we want if we're lucky. Let's assume maximum luck. Let's assume that we know what type we want. Let's assume that we can figure out the type of the argument. We know that because the function doesn't have a dependent type, one argument's pretty much as good as another. So there's no point in bothering about which particular argument we've got to figure out what type the function has to have. So this much isn't so bad. But the moment we become slightly more engaged, with obsessive color coding, then we're in the situation where this type, if we're lucky enough to have it, we only get one particular instance of it. And if the game is to guess this type, we have to figure out what the general abstraction of X inside tau is, just given one particular example of it. So if the information happens to be flowing in that direction, we are thoroughly stuffed. So, next message, don't give up hope altogether, but do keep a more careful handle on the direction in which information is flowing through type systems. Okay, let me also observe just some classic examples of pre-dependently typed but post-Hindley-Milner things are not quite all the way they used to be. The composition of show and read. What goes wrong there?
It's too polymorphic.
Yeah, it's ambiguous, right? That's one of the things, the corners of the Hindley-Milner type system you don't often get to step on, is that sometimes a type variable needs to be thrown in. It stands for some unknown thing. You hope to solve it by unification, but you don't. And still, it doesn't show up in the type of the resulting expression, right? Show, propose, read. Show after read is string to string. No type variable. The type variable in the middle isn't present in the type of the whole thing. Now, this is the joy of parametric polymorphism. When everything's parametric, if you don't know what it is, that's okay, because you can't possibly care what it is. However, the moment you introduce some ad hoc polymorphism, then which type we have here, like we need to know how to show and how to read it, which type it is, it's going to matter. So once we do that, we've lost complete type inference in the sense that there's a genuine ambiguity that has a semantic impact. Whereas previously the ambiguity existed, it just, by parametricity, didn't have any impact. Okay? And then here's your other classic. It's polymorphic recursion. Here's my favorite example. You've got a lovely scope-safe representation of lambda terms, where the body of a lambda, so the type variable, the parameter, represents, or rather I should say, the uniform index. It's not a parameter, and that's the point. Represents the set of free variables which may occur in terms, and then when you go under a lambda, you throw in an extra free variable by maybeing that type. And then correspondingly, when you're writing the rename operation, which takes some function mapping variables to variables, when you go under a binder, you have to adjust the renaming operation, and you do that uniformly by the functoriality of maybe. But the point is that the recursive call to rename is being made at maybe of whatever the alpha parameter was before. And crucially, the deal is with definitions is that you assume a uniform type for the thing you're defining. You see what type it is, you check the recursion, assuming that uniformity, and then you do the generalization of the let afterwards. And here, you need the thing to be general even during the process of type checking the definition. And once you let that generality in, you lose the ability to infer types. So what's going on is, in all sorts of little ways, we were chipping at Milner's coincidence, making some type annotations necessary. Oh, and the other thing, of course, with show compose read, if you do enough type annotation for that, then all of a sudden you're relying on a type class mechanism, which is doing instance inference, which means that there is some term which is unseen and synthesized by a machine, and which is retained by code generation. So that's another piece of a wobble in Milner's coincidence that was already happening, a long time before dependent types became the obvious threat that they are. I mean, Milner's coincidence was busted, and it wasn't me who busted it, right? I'm just trying to help you live with it, because I never wanted it. Okay. So yes, so what's just around the corner? Here's some speculative Haskell fiction. Some of these things exist already. You'll recognize them. So this thing exists already. Actually, this is what I meant by the disembodied voice of Simon Peyton-Jones. When you get a type error from GHC, you should think of that as Simon talking to you. And there are situations where when you are abstracting over a type, and because of the persistence of Milner's coincidence, it is compulsory that the thing which is being abstracted over in a dependent way is not present in your program. Whether you want to write it or not, whether you know what it is or not, it has to be invisible in your program text. And that is Simon saying, no, I want to guess. And if only there was sometimes, so people do all sorts of things. They have to invent these proxy types and stuff like that in order to be able to give Simon enough of a clue so that he can guess the thing that has to be invisible. Wouldn't it be just much easier if you were allowed to say what it was? So this type will hopefully come into existence soon. Note the distinction between the dot of inscrutability of invisibility and the arrow of visibility. So, same quantifier. Quantifier means this, so the for all now means something rather special. It means erased at, by code generation, which has nothing to do whether it is a machine or human supplied piece of information. That's told to you by the dot and the arrow. And it's not only then that we have knocked these distinctions a bit out of whack with one another, they're just completely orthogonal. Meanwhile, we introduce, so down here, we still have our good old function space that we're familiar with, which is a vacuous quantification of runtime stuff that's being given explicitly. But hey, in this picture, we now have the fat arrow of constraint. We are seeing this is the arrow of runtime stuff, which is invisible and supplied by a machine. But meanwhile, as well as retaining this stuff, we're going to learn to retain this stuff, which is introduced by the pi quantifier, which tells us that what we're getting is real runtime stuff, and it might be runtime stuff that the machine is clever enough to guess. Hooray, program inference! Or it might be runtime stuff that we're going to give explicitly, but both of these variations ought to exist just as those. And while we're talking about it, let's not be so presumptuous as to imagine that the domains of these quantifications are anything particularly special. I mean, on the one hand, we've already seen vector zip today, where it's perfectly acceptable for the length of the vectors to be a purely static quantity. But there will certainly be situations, for example, let's say you want to make just, some number of copies of an element to make a vector of the given length. Then you will certainly need to know that length at runtime. So certainly for things which look like data, there are roles for both for all and pi. And let us also consider the situation when we're abstracting over types. Right? Current practice is for all abstractions over types to be purely static things and correspondingly parametric. But we spend a lot of time and a lot of energy trying to figure out how to write data type generic programs, which essentially rely on having some runtime representation of types. And there's an awful lot of machinery in Haskell, for example, with data.typable and so on, which is all there trying to generate the things that can exist at runtime because types can't. Why not just abstract types with the pi and work with the types themselves? So that's a problem which is currently receiving a great deal of attention, how to make data.typable survive the new regime. And that's missing the point of the new regime. Okay, so yes, here's another just little entertaining old story. This is the downfall operation. This is just to remind you of, first of all, that some numbers, some invisible things really are runtime relevant. Right? If you know, so this is the vector of numbers, which is below its length. So if you ask for the vector of length 5, the downfall of length 5, you should get 43210. And of course, it really matters which number you get at runtime. Head of downfall. If you pick a downfall that's a non-empty length, will always be some number. Just, it's the same deal as show after read. Yeah? It's some number, and you need desperately to know which number. Right? But it's a nice thing that although if you know the type in advance, you don't need, for example, here, at this use site of downfall, you don't need to give the length, because we know, because we've got a cons, which I'm writing as a comma here, it's got to be one less than this length. At the same time, in order to give the program its operational behavior, it's necessary to pattern match on this thing which we can't see. So it's another situation where it's not just a question of some things are always invisible, some things are always visible. It's that sometimes you need to look at things in order to define a function, but not to use it. Okay, fun stuff. Okay, so where have we arrived at after Milner's coincidence? So I've drawn the beginning of a picture and reminded myself what needs to go in it. Right, so distinction between syntactic categories, term and type, gone. Waste of time. Always was, in my opinion. Now causing more trouble than it was worth. Right, what else? Quantification. Vacuous quantification. Well, if you want to be kind of allow dangerous programs, you might want to keep them out of your type system. But if you're working in a total setting, there's no point in having any quantification that isn't dependent. I mean, that's just like saying, there ought to be some stuff that types don't talk about. So, you know, why would we talk about it if types couldn't? Okay, but especially as we're interested in type inference and essentially the art of the possible for humans and machines, we should pay attention to this distinction. And we need to think about what happens as far as visibility and code generation are concerned. Well, let's just play that game. I'm just going to draw the code generation line in roughly the right place. Let me see if I can get it right. Yes, I kind of want it here. Let's see, which side of it is which? Well, I kind of hope that I can label it any way I like, but we should consider which are the fun parts, right? You know, isn't it? Don't we want to maximize this region? The stuff that we write. Or rather, the stuff that the machine writes for us, but is actually used at runtime. And similarly, you know, if we are able to write things which live here, so this is really type as spec. And this is details. You know, the more you've discovered, so these are the details that you have to write. And these are the bits of type information that the machine can get. Well, maybe, hopefully, at least they're going to be the following the plan stuff. Right, so this is, we kind of want, this is var rule stuff. Yeah? Where there's some sort of information that the machine needs to figure out to see how a particular well-specified thing is being instantiated. Okay, and then what happens as far as visibility is concerned? Well, we would certainly like to ensure that, well, anything which is generated by the human is likely to be visible. Well, unless you're using cock, that is. I mean, somehow the document that we write and that we read should be the representation of our effort. But we should not rule out the possibility that some of the document we generate when we're working with a type system is visible but generated by the machine. This is what happens when you're writing IDRIS programs, AGD programs. There's some type information which enables the machine to generate some of the visible stuff. Okay, how am I doing for time? All right, actually. Could be a lot worse. Okay, so let me kind of talk a bit more about direction flow in type systems. I've now moved to talking about kernel-dependent type theory. So here's the kind of expectation we have in a bidirectional system where the very judgment forms, and indeed the separation of syntactic categories that I would choose to make, is distinguishing between those things which have a type proposed up front and those things from which we can synthesize a type. So the typical situation is that if we have a type, we can see that as a menu for building canonical values of that type. So the menu for PyType just has one option, that's lambda, and then you choose what to call the bound variable. The bound variable goes into the context with the type that was sitting there coming in the domain of the PyType. Doesn't need to be on the lambda because you already know it, and you know at what type to check the body. And you keep going until such times as you stop giving canonical components. And now you need to make something out of the things that are in your context. So you need to change direction. And this is the point where you say, okay, I'm now going to synthesize, I'm going to give a term whose type can be synthesized, and when I know what type it's got, I'll compare it with the type I want, and hopefully the type I've got will be good for what I want. And this subtyping relation is whatever you think you can get away with. I recommend alpha convertibility and no subtyping relation whatsoever. Actually, that's a slight lie, but at least it's a good start. Yes, here's the point where the constraints get introduced that we hope some constraint solver will solve. And the more of them are equational constraints, the better time we'll have of it. But you know, if we were going to do subtyping, here's where we would do it. Okay, so now we're playing the other game. We've got a bunch of things in the context, and they all have types. So we can certainly synthesize the types for those things, because the context says what types they have. And then we can use those types as the menu for how to exploit those assumptions that we possess. You know, what eliminations are possible. That's why I've chosen the meta variable e. So, for example, if we can discover that something is a function, then we know how to make use of that function. We merely need to check that we have a suitable argument of that type. And then we know how to instantiate the return type with a typed thing replacing the variable. And you'll notice that certainly nowhere on this slide have I explained, I mean, S is in general Little s is in general a thing whose type is checked. The variable is a thing whose type is synthesized. So it's not even syntactically valid to consider substituting little s for little x. What on earth is going on? Well, there are various things that might be going on. One thing you might do to explain what this operation is some sort of hereditary substitution, where you kind of kill off all the computations that are introduced by the substitution during the course of substitution. If you want to explain how that works, you need to know why your language is normalizing. Which, might be, it might not be, but it might be nonetheless convenient not to have to explain that at this point. So let me introduce something to deal with that. So yeah, sorry, let me just introduce naming conventions. This COD rule, COD is short for change of direction. Not supposed to be something fishy. Here, doc is COD backwards because it's the change of direction in the other way. Also, it's documentation because it says, well, if you've got a term whose type you can only check, well, you're not going to be able to synthesize a type for it without a clue. But why did you write a clue? Why don't you propose a type for little t? And then all you need to do is check that big T is indeed a type, and then that little t is indeed a big T, and then you can synthesize a type for little t, namely the very type that you offered. And that's how you can do the change of direction. And this thing, which is the sort of thing we were substituting for the variable, makes perfect sense. That substitution is now okay. We have to tweak the beta rule just a little bit. The beta rule, the only way we can form beta redex is to say, well, we have a function with a type annotation, and it's being applied. And that's going to reduce to the instantiated body at the instantiated type. So what we're really saying here is that type annotations mark the cuts, and cut elimination turns a cut as a big type into lots of cuts at smaller types. We hope. So that's the situation. The type annotations mark the places where computation still hasn't ground to a standstill, and it tells you the type at which computation is happening. And then this other computation rule, the gamma rule, for garbage collection, is just telling you that whenever a computation boundary has made it all the way out to a change of direction, we can throw away the type annotation because it's finished. Okay? And then all we need to do to recover type theory as we know it in this bidirectional situation is to say that when we're checking a type, we are allowed to do a little bit of computation first. That's to say, if we've got a type, we're trying to check it, and it doesn't look like a pi type yet, for example, we can compute it a bit, and if we can get it to be a pi type, then we can carry on and check our lambda. Similarly, if we are synthesizing a type, let's say we synthesize a type for something that we hope is going to be a function, but the type of the function doesn't look like a pi type yet, then we can compute it a little bit. Before we carry on with the rest of the type checking process. Okay, so I should try and get off stage. So I'll not digress via effects. I'll say something about types and type schemes. Type schemes are still extremely valuable things, but I recommend keeping them out of your kernel theory because they're extremely difficult to guess. I mean, one of the things that we're now in the situation of trying to do is to solve equations for variables that stand for stuff if you can have variables that stand for type scheme, then there's a risk that you might have to guess what type scheme ought to be given to some function symbol. And then, let's say you're in a situation where you have a function that has an unknown type scheme. You don't know how many hidden arguments to give it, because you don't know its type scheme. So, at that point, elaboration, the decision, you have to make an unmotivated decision there. You might wait and hope that something else will determine the type scheme. Or you might just guess, oh, it doesn't have any implicit arguments. And you might then be wrong. So I recommend just making sure that doesn't happen. And one way to do that is to make sure that only things which are going to be made visible and used explicitly get type schemes, whilst everything that is hidden has a type. And there are interesting questions. When something is hidden, how do we guess what it is? Quick survey of that. I just want to point out that we got terribly used to, thank you to Robin Milner, a situation where unification always had the answer yes or no, because types were a first-order theory and no computation happened in types. So that's just sort of unification nirvana. Nothing hard ever happens. Whereas life is more difficult in two different ways. One, we're not working in a first-order theory anymore. Some of the things we don't know are functions. And the art of the possible comes essentially from Dale Miller, which is to say, when you see an equation that's supposed to tell you what a function is, can you figure out what the function is? And if the equation looks like a definition, then you know what the function is. I mean, so straightforwardly, if you're trying to solve an equation, solve for x equals t, that equation looks like a definition of x. Yeah. If you're trying to solve a function, and you're trying to solve f of x, y, z equals t for all x, y, and z, well, doesn't that just look like a functional program, which you know how to compile with a lambda? That's the message. But also, once we have, in particular, recursive programs, the programs which occur in types, they get stuck. So we now are no longer just working in the constructor theory. Even when we're working in a data type, we have to solve equations that might have some constructors around, but also have some functions like, addition or whatever it happens to be, that have got stuck. So how do we solve those equations? Much harder problem. But I guess the more obvious thing really is to say there's more than one way to fill a hole. Unification is not the only game in town. And a big mistake, which lots of our comrades are making, at least I think it's a mistake, or at least unpalatable, is that since all unknowns are to be solved by unification, every method of solving unknowns has to be added to the unification algorithm. So, for example, in canonical structures, one field of a record. You have an unknown variable of type record. Carrier of x is this, and now you can guess what x is because you know one field. Okay, so just watch that. I guess I will finish with this last observation that when you work in this world, design errors are the new type errors. When you propose types up front, the biggest danger is that the type you started with was a really bad idea. And the question then is, once our initial rush of enthusiasm to inhabit that type has been thoroughly thwarted because it was the wrong type, how do we recover? And so we've got lots of technology for banzai, we're refining the problem. We've got no technology for when we realize we're just banjaxed. And that's where we need to make some real effort.
and then going for coffee because we are eating out time from our coffee break. One question? One brief question? Conor, you'll kill me. I discouraged your audience.
Yeah. I kept them from their coffee.
I think then one comment, which is a subtle talk can't be met with an unsubtle short question.
But Dale Miller's work you meant, yes?
Yeah.
What in particular, Dale Miller?
So in particular, a paper that James shoved in front of my face many years ago, which is about the sort of unification under a mixed prefix, where you can't solve all the higher order equations, but you can solve the particular benevolent ones, where a function is applying to things which look like patterns. And if you've got a bunch of equations in a function, and you can check that the patterns make sense, then you can figure out what the function is.